Let's look at theorem 2.3. If alpha is a measure of inscribed angle, so in the picture, alpha at vertex A is an inscribed angle. Inscribed angle means angle with vertex on the circle. Subtending chord BC over circle. So this is chord BC, and this is the inscribed angle subtending chord BC. Then the locus of all points. The locus means a set of points satisfying certain property. What property? From which the chord BC is seen by alpha is the arc BAC. So that means the vertices of the angles congruent to this angle alpha must be on this arc BAC. So if it's not on the arc here, this angle formed by these two line segments cannot be equal to alpha, either inside or outside. So if we want this angle to be congruent to this alpha, this point P has to be on the arc BAC. So it could be either here or here or here or here. So it can be anywhere on this arc, but not inside, not outside of the circle. So how to prove the case? We want to use the indirect proof. So first we say if it's we actually already know if it's on the arc, that from the last theorem, the corollary 2.1, if they share the arc, for example A and B, these two angles must be congruent. So then in next theorem 2.3, actually we want to prove these are only angles, congruent angles. So if I kind of move this point B out of the circle, and we join X and B and Y and B, it cannot be congruent to A, or move this point inside the circle, and then the angle cannot be congruent to A either. So it has to be exactly on the arc, on the circle. So now we already know if it's on the arc, they must be congruent. So we want to show if it's not on the arc, they cannot be congruent. So there are two cases. It's either the point, if it's not on the arc, it's either inside the circle or outside the circle. So first case, inside the circle. We want to prove BPC is not, if we use beta to denote the measure, we want to show beta is not equal to alpha. And the same thing here, if P is out of the circle, BPC, if this is gamma, gamma is not equal to alpha either. So what we do is we're going to, if it's inside the first case, we're going to extend BP, this line segment BP, intersecting the circle at point Q, and we connect to C and Q. So we get this triangle PCQ here. And in the second case, because in the second case there's we don't say extend, because we just connect B and P, and because P is outside. So when we connect B and P, they must the line segment BP must intersect the circle at a point. We also call it Q, and then we can also connect C and Q. So we get these two triangles, either PQC or this triangle PQC here. So now if we look at the angle at P, BPC, this is it's an interior angle of BPC, this triangle BPC, but be careful here, we're not looking at the triangle BPC, we're focusing on this dotted triangle with two dotted sides, PQC. Focus on this triangle, then this angle at P here, beta here, BPC is called what we call the exterior angle of this triangle. So by one of the theorems we proved before, the exterior angle must be greater than the remote interior angle. So beta must be bigger than the angle Q right here. And we know angle Q and angle alpha are congruent because they are both inscribed angles and they both share the common arc BC by theorem 2 corollary 2.1. These two inscribed angles intercepting the same arc are congruent. So alpha and Q are congruent. Or you can say angle A and angle Q are congruent. But angle P here, the beta is bigger than Q, which means beta is bigger than alpha. So we proved if P is inside, beta is bigger than alpha. Similarly, the other case what we do is we look at this triangle, still look at the focus on the triangle PQC with one dotted lines side. And the angle BQC is still the exterior angle of this triangle. And the gamma, again, this angle is BQC. I'm sorry, actually, BQC, this angle BQC, Q is on the circle. So BQC is the inscribed angle. Angle A is the inscribed angle. These two inscribed angles both intersecting the same arc BC, so they are congruent. And also BQC is the exterior angle of this triangle PQC. The exterior angle is always greater than the remote interior gamma. So we get the angle at Q is bigger than gamma, but the angle at Q is the same as alpha. So we have the angle BQC is greater than gamma, which means alpha is greater than gamma. So if P is inside, beta is greater than alpha. If P is outside, alpha is greater than gamma. So that means if we want them to be equal, this point has to be on the arc BAC, anywhere on the arc. So combining the last corollary 2.1 and the proof here of these two cases, we proved theorem 2.3. The next corollary, any angle inscribed in a semicircle is a right angle. So if you look at the picture here, this is a circle and this is a diameter. So diameter will cut the circle into two semicircles. And the angle inscribed, so this, for example, this angle is the inscribed angle because this point is on the vertex is on the circle. So this inscribed angle we want by corollary 2.2 says this angle must be 90 degrees. So this is a very interesting, very useful property. If this chord here is diameter, but if it's not a diameter, of course it's not. For example, if you look at here, this BC here is not through the center, so it's not a diameter, so this alpha cannot be 90 degrees. But here, if this chord is diameter, and we know the diameter is 180 degrees chord, and because this we by theorem 2.2, this 90 degree angle subtends the arc of 180 degrees. So this chord, we kind of have to prove two directions. First of all, if this is diameter, this angle must be 90 degrees. Secondly, if this is 90 degrees, conversely, if this is 90 degrees and this arc, we must be able to this chord here must be a diameter. So the first case is very easy to prove. If this is a chord, if this chord is a diameter, it's 180 degrees, and we know the inscribed angle is half of the arc, or half of the well, I guess I should better say half of this arc, and half of this arc, because this arc is 180 degrees. So if you join the central angle, what's the central angle? This is the center right here in the middle of this diameter. And what's this angle? This angle is 180 degrees from here to here, 180 degrees. So this arc is 180 degrees. If this arc is 180 degrees, the inscribed angle must be half of it, which is 90 degrees. So this can be proved by one of the theorems we proved, theorem 2.2. The measure of inscribed angle is half of the measure of the intercepted arc. So the conversely, if we know this is 90 degrees, can we say this must be a diameter? Yes, because kind of reverse what we just proved. If we know this is 90 degrees, it's an inscribed angle. So by theorem 2.2 again, what is the measure of the intercepted arc? This arc must be 180 degrees. If this is 180 degrees, and then this central angle has to be a straight line, 180 degrees. So that's why if it's a straight line, that must be the diameter. And because central angle always through the center, and if it's also straight, that must be the diameter. So we proved this case. So if we have inscribed angle which is 90 degrees, then the chord must be this chord must be a diameter. Well, we can say this triangle is inscribed, this angle is inscribed in the semicircle. Well, if it's a semicircle, this angle must be 90 degrees. The next example, 2.1. This is the example on page 83. We're going to use corollary 1.2 we proved before to solve this problem. So in this problem, there's so many lines here. So first of all, we have a diameter. This is O, which is the center. We have a diameter here, and we draw another diameter which is perpendicular this diameter. So that we have two diameters that are perpendicular to each other. So this is 90 degrees at O. And then nextly, we look at OC, this line segment, from the middle point M, and we draw a perpendicular. So this DE can be considered as the perpendicular bisector because it's perpendicular to CO. It's also bisecting CO because M is the middle point. So that's all given in the problem. And then we can connect B and D and connect B and C. So we got two angles, alpha and beta. We want to find out the measure of alpha and beta. We found how to find alpha and beta. So there's many angles. We want to use the theorems we learned before in this section, and also theorems we learned before. So first of all, notice alpha and beta. Because this point B is on the circle, so that makes ABC an inscribed angle. An inscribed angle, alpha plus beta is inscribed angle. So inscribed angle is equal to the measure ABC. Again, the angle ABC is equal to alpha plus beta, which is a inscribed angle. So by the theorem we proved before, the inscribed angle is half of the intercepted arc. So intercepted arc, this arc here, ADC here, ADC. Is going to be 90 degrees. Why is ADC 90 degrees? Remember the definition of the measure of our arc. The measure of arc is the same as is defined as the measure of the central angle. So if we look at the central angle has to pass through the center. So AOC is the central angle. That is because this is 90 degrees. We know they are perpendicular to each other. So if this arc ADC is 90 degrees, the inscribed angle must be half of it, which is 45 degrees. So this inscribed angle ABC, it's also alpha plus beta, that's 45 degrees. So first we find out alpha plus beta is 45 degrees. And next we know this DE is the perpendicular bisector.